Hello and welcome back to Calculus 3. This is exam 3 review, right? We're just going to go through the shopping list of things you need to know. And also going to take a look at some generalizations regarding integration. So the whole exam is on chapter 13. And since the problems tend to be very long and painful, right? We'll probably have anywhere between 6 to 8 problems on the test, and again, depending on the spice level, right, we might have the replacement question at the end that you can use. So chapter 13 is on integration, and you will need to know, let's put just know how to, and then let's go evaluate double and triple integrals. So that will be the first order of business. And then set up double and triple integrals. Now this is going to branch out. This is going to branch out. Your double integrals, you will need to know rectangular. That is when you have all 4 numbers, right, as limits, rectangular region. Then you also have general, where the inner ones have function, and polar, which is the 13.3. So this is your 13.1, 13.2, 13.3. Triple integrals go on the rectangular, go into general, that's with the functions, go into cylindrical, and goes into spherical. So know how to set up double integrals and then know how to evaluate all of these integrals. Now, know how to convert rectangular into polar, cylindrical, spherical, and that conversion is obviously the first one is for the double integral, and then the bottom ones are for the triple integral. So conversions. Now, know how to compute volume using double integrals or triple integrals, and we'll discuss that. Know how to compute center of mass formulas given. If I put a problem for computing center of mass, which is extremely important for your mechanical engineering realm, since it's so specific and not for all students, I will provide the formulas. However, if you are a mechanical engineer or civil engineer, and you are relying on me to provide the formulas, please quit your major right away, because that's your life. Those formulas are your life. All right? That's that. The disclaimer, the fine print, okay? So, right, use the formulas I provided and switch to major next day. The last part would be to use the change of variables plus Jacobian to go from one realm into the next, right? So transformations, this is called a change of variables in multiple integrals. Change of variables in multiple integration, which assumes transforming region, Jacobian, and yeah. And computation. By popular demand, the transformation is given. Unless you request not to give you transformation, in which case you would have to find it first and then deal with the rest. So that is the shopping list for the exam, and I said 6 to 8 problems. You have 6 bullet points over here, but don't forget that the second bullet point branches into 7 things. It's all right. This is not 6 bullet points. This is actually 12 bullet points. Okay. Now, I just want to put the entire calculus in perspective, Calc 1, 2, and 3, and with that, clear up a lot of stuff for double integration and triple integration. So we're going to start with the Calculus 1 concept of area under the curve for f of x, where area was found as integral a to b f of x dx. And you see that it's a two-dimensional concept. One dimension comes from the function, the other dimension comes from dx. So f of x acts as a height, and dx acts as the width. So height times width gives you the area. Now, you move at the first lecture of Calculus 2, you move to the area between two curves. You have f on the top and g on the bottom, and your area is between a and b of f minus g dx. Again, when you go f minus g, that gives you a new function, call it, I don't know, r, whatever, and that gives you one dimension times dx gives you the other, so it is area. Now what we are going to do is we are going to upgrade this in a double integral, and we are going to say that you can take the double integral from a to b and then from g to f times dA. So we can calculate the same thing, which is area between two functions, by putting those two functions in the integral using dA over here and not putting a function inside the integration. Just put number 1. So now your dA is either dx dy or dy dx, which provides two dimensions. Since the integrand is 1, that doesn't bring a dimension, and you have the area. Now remember, when you integrate 1, let's say this is double integral 1 dy dx, and you have your function g over here and a function f on the top, and then you still have a and b. When you integrate 1, you will get y, and that will be computed from g to f. Do you see how that's f minus g, and it collapses to this formula immediately, right? So that's the magic link between these dimensional equations, right? It's just a different way to write the same thing. Now, in the next step, next line, I'm going to put the double integral with the function in there, and that becomes the volume now, because you have the dA, which is 2d's, and then the function in there is a third dimension, so it's a volume. So I hope you've seen this little manipulation here that these two equations are equivalent. Now I'm going to go one dimension higher, and I'm going to say that if I have some kind of domain in x, y, and I build some shape of top of it, right, whatever the shape is, in a z direction, I can compute the volume as I take the double integral a to b, maybe f to g to f, you know, that doesn't have to be. And then I put over here the function, right, the function h, and that function h is in terms of x and y, and then I have dA. So dA is already 2D, times this is 3D, so it's volume. Now, because I put the function here as h, it guarantees to have a flat bottom. Okay? Because you have h of x. What I'm going to do in the next example is I'm going to, you know, pick some domain, whatever, but then I'm going to have a function that it's, I don't know, whatever. Draw whatever kind of function you want. It doesn't matter. So there is some kind of domain in x, y, but now you have h and k, function h on top, function k on the bottom of x, y. And I hope that you see that this is just one dimension higher from the area when you have a function on the bottom and function on the top. So now the volume is going to be the double integral of a to b and g to f. This is the domain. And then you are going to have h of xy minus k xy dA. Now remember what I can do? I can stick these h and k functions in the limits of the third integral. So volume can also be represented as the triple integral a to b, f to g, k to h dv, where you have 1, right? So now these are of x and a y, and f is only in terms of x, and g is only in terms of x. So I hope that this progression from a single integral with f minus g to a double integral where f and g are in limits, I hope that you see the same progression here. It's the same. First two integrals are identical, and then your top function minus the bottom function, which is the top mushmash on the object you have and the bottom mushmash you have, right? They don't have to be flats. It's top minus the bottom. So you know that when you solve the dz, 1 dz, you will get z, and it will be h minus k, which collapses to this integral right away. Right, the first calculation goes there. The next part, yes?
So if you tell us to calculate the volume, we can use either or?
Yeah. For your egg, you can use either or on the project. It's due the day of the final exam. I hope you're pretty much done, because the final is in 2 weeks, and you should be preparing for that, not typing the 10-page paper on the day of the final. The last concept is the 4D. I'm going to have this object represented in this integral times the temperature distribution function, which I'm going to plug in here, or density distribution function, or whatever else. And that creates a dimension there times dv is the 3 dimensions there, becomes 4D. So this plus temperature or density or whatever, right, is going to give you the 4th dimensional thing. So I have a triple integral of some function here. I don't even know what to put now, which letter I haven't used. How about for a function, what would be good? W of x, y, and z dv, your a and b, your f of x and g of x. Your g of x and f of x, much better. And then your, what did I use? K over here, x, y, and h, x, y. And that's 4D, bulk. I can do this progression forever. Right? I can have two densities, right, subtract each other, which, right, maybe you mix two things, whatever. That brings in the fourth integral, and then whatever the fifth dimension would bring in, right? We can mathematically, we can chain this into infinity if we wanted to. For purposes of application, we don't need to. So we stop right here, right? And this is everything we covered in our Calculus 3 class. So starting with the double integral, which is just the upgrade of the single integral, and then slowly progressing into triple integration. Now, we also have those levels that I mentioned up there in terms of rectangular, general, and then polar. And then I had the other set, which was rectangular, general, space them out, cylindrical, spherical. Now, what does this pertain to? All of this pertains to the shape of the domain and which way your integrals and their limits are going to be presented. Okay, so for rectangular, so clearly these guys over here, let's use blue. These guys are 2D. These guys are 3D. Now, that's a 2D and 3D let's put in the setup. Nah, that's bad. 2D, 3D domain. Okay, that's much better. Because when I say rectangular, that means I just have A, B, C, D. That's what it means. I have numbers around and I have dA. Now, I'm going to ask you, do I compute area or volume with that? And you're going to jump area because I don't have anything in it, but it could be volume as well, all right? Because I could put a function in here. Rectangular here doesn't tell me anything about dimensions. It doesn't tell me anything about whether I'm computing area or volume. It tells me that I'm supposed to put 3 and 7 and 0 and 2, all right? Just numbers here, which says that the domain is rectangle. Now, if I put something inside, I will be building up the object over that rectangle. We talked about the stencil, and then that will be 3D volume calculation. But if I don't put anything, I'm just computing the area of the rectangle that is in the limits. So we are not talking about dimensions and what concept we are computing by this integral. Rectangular, general, and polar actually pertains to the domain and then what it has. So over here, we are looking at the A, B, C, D in the domain. Now, what does the general pertain to? General pertains to the integral that has A, B, and then F and a G. Let's say of X. Again, dA. I can put the function inside and compute the volume, or I can keep the function out and just compute the area of the domain. And what you get here is the domain that has the function f on the bottom, function g on the top. Again, if I put a function in, this becomes a stencil. All right? If I don't put the function in, I'm just computing the area of the intersection over there, or the slice. Polar clearly has its own 0 to, sorry, not 0. We'll go alpha to beta angles, right? And then what's on the inner? Radius 1 to radius 2. We might have something, we might not have something, but the string is r dr d theta. You have to remember r dr d theta. Now you studied this formula in its single integral form in Calc 2 in Chapter 10, and you studied the double integral form in Calc 3. It's the same formula. What you have here are the polar regions, so the graph might look something like that. Let's take one petal of a flower. It's good enough. Now, what is the same story for a rectangular, general, cylindrical, right, for the 3D? Well, it's the same thing. This would be the triple integral dv with a, b, c, d, e, and f. If you just have numbers around and you have no function, you are calculating the volume of this room. This is a box. So what you see over there is computing the volume of a box. Now, if you put some kind of function in it, then it's going to go 4 dimensions and do something else for you. So this is your A, B, C, D, and then over here, E, F. General is going to introduce the limits as functions. So we have A, B, always numbers at the end. And then over here we're going to have F and a G in respect to X only. And then maybe H and K in respect to Y. And we already talked how this could be, the way it's written now is just volume. If you add the function inside, it computes the bulk, right, 4D. Now, for cylindrical coordinates, we have the polar coordinates and the z on the inside. And this comes in 2 flavors. There's a flavor 1 and the flavor 2. It's like vanilla and chocolate chip mint, all right? Chip mint or whatever, mint chip. What's it called? I should know, that's my favorite, mint chip. Yeah, we talked about the stuff. No candles. Mint chip, yeah. So, cylindrical is going to have alpha and beta on the outside. And then it's going to have your R1 and R2, which is the radius for dr. And then it might have A and B, because the string over here is R, dz, dr. Well, no, we did the zr, dr. Okay, well, let's put it in the order that was in the book. So the zr, dr, d theta. It doesn't matter whether this r goes in front of dz or outside of dz, because it's r, right? So in terms of dz, that is a constant. Or the triple integral alpha, beta, r1, r2, and then over here you have the f and g of x. which will be transformed into R's. dz, r, dr, d theta. So cylindrical can have any of those. And finally, spherical is the one that we have alpha and beta, and then anyone? Who cares, right? Let's go with gamma and delta, and then R1 and R2 for the radius. And then we might put something in here, we might not. And then we use rho, right? Rho squared. Sine, I hear you guys, sine phi, d rho, d phi, d theta. So you see that the Greek letters alpha and beta for angles are angles of theta. Gamma and delta are are angles for phi. And then you have the d rho, which is the radius. So radius rho. Well, we use r throughout, decade of your education. We use r for the radius, and then you get spherical coordinates, and just for spherical coordinates, rho. So that's your r. Okay, that's your r for polar coordinates. I need you to see the polar coordinates, dr, d theta, with the r over there, one of the r's. So r, dr, d theta, that's the polar base. And then the spherical extra stuff, r sine phi and d phi. Right? That's the build-up on the things. So hopefully this puts all of the integration, no matter the dimension, no matter the concept you're computing, in perspective, and then sorts out the wording, rectangular general, which pertains to the domain and the setup of the integral rather than to the product it gives at the end. Does it make sense? So study that a little bit, put things into perspective, so this stuff will be much easier. To convert from one system to another, you either know the conversion or you don't. There's nothing I can do about that, right? You have to remember that x is r cosine theta, y is r sine theta, r is square root of x squared plus y squared, and those conversion factors that actually you should be dragging with you all the way since Calc 2, right? That's not new. I promise not to invoke the trig things when you have to actually make up stuff for spherical coordinates, but the straightforward spherical coordinates conversion would be okay, right? If I set up the integral in rectangular coordinates, that obviously cannot be solved in any way, and you see that you have the cylindrical form of it, changing it into a basic no-brainer integral is okay. So that is a question, should not be an issue for you guys. One more time for center of mass. I will give the formulas, but then I also gave one formula to my Calc 1 students, and just 70% of the entire class went nuclear on it. Said, I really don't know what to do with this. And I said, of course you're not going to know what to do with this, because I told you I'm going to give you the formula, and you disregarded the entire section, and then when I gave you the formula, you haven't even spent 2 minutes with that section at home to figure out where to plug things in, right? So you still have to study this section. I'm not telling you not to study section. You must study the section to know, because I will give you the formula now. If you haven't studied, you have no clue what goes where in that formula and what's what. This is going to be a whole bunch of piled up numbers and expressions that will mean nothing. So you have to study the section, and you are not required to memorize the formula unless you're a mechanical engineer or someone who's actually going to use that very, very frequently. Change of variables, I will give the transformation unless, again, someone else mentions that I shouldn't, and then I will scrap that off, as I thought. Very good. Jacobian, right? You will have to memorize that Jacobian is the matrix of partial derivatives, and you will use that. And I think that right, you should be able to integrate square root of x. You should be able to use basic u substitution from Calc 1. I'm sorry for disappointment, but I'll try to steer away from, by parts and partial fraction decomposition and trig sub and stuff like that, because these problems are long enough even without that. So we'll probably stick to basic integrals, and we'll stick to u sub, right? But nothing insane. I mean, if you don't know that 1 over 1 plus x squared gives you arctangent in integration, then, I mean, that's basic formula. That's not us invoking 16 methods of integration to calculate the basic integral. It's just you know it or you don't. And spare yourself embarrassment of making comments about ease, because happened in the past and it didn't go well. So yeah, when you see integral that contain e, you should write thank you next to it, because there is no easier thing to integrate, right? Integral of, what is the integral of e to the a x? Exactly. ax over a plus c. You can't get anything. You get to copy the same thing and just divide by whatever number you get there. So you can't have anything easier. This is easier than integrating x squared, because for x squared you actually have to go 2 plus 1 is 3. Right? There is a process of computation in the polynomials. For e to the x, you just cut and paste, like Control C, Control V, and then you just add this over a underneath. All right, so that's technically it. I will, I guess, see you all Monday for the exam. Don't forget